Hello everybody, welcome to the World of Control channel. I'm Mohammed, and in this video I want to linearize the dynamics of our system that we modeled in the previous videos about the system of inverted pendulum on a cart. First of all, make sure that you subscribe this channel because I'm going to make a lot of videos about modeling different systems and designing different controllers for simple systems actually and also complicated ones. Thank you very much. So let's get started. As you know, in the previous video, we started to extract the dynamics of the system of inverted pendulum on a card, and we actually derived the equations of motions of our system that you are watching in this slide here. These equations are nonlinear equations because we can see that we have cosine functions in our equations and also multiplication uh, between the cosine of theta, for example, to x dot, at that is our velocity. For now, because we want to actually design an observer for our system, we need our system to be linearized. So first of all, we need to assume our space variables, such these variables here, theta x, theta dot, and x dot, as x1 to x4. And with respect to these variables, we can see that x dot 1 is theta dot, so is equal to x3, and x dot 2, that is x dot, is equal to x4, and x dot 3, that is theta double dot, is derived with this equation. And if we change the variables to x1 to x4, we can derive our state space equations like these two equations here. And for linearize our model, we need to use these two equations. We need to derive and extract A and B matrices with these equations. Because we have four state space variables, we have a matrix of 4 by 4 of A, and because we have two inputs, we have 2 by 2 actually matrix here for our B matrix. So let's start to code these equations here to actually extract the linearized model here. So let's start coding in Matlab. I want to clear all the variables in the workspace. Oh, sorry. And close all the plots that we have. And for now, we need to actually define the parameters of our system. So I will use sims m l g, and let me bring our equations to see what we have in our dynamics. We have f as an input, tau as an input, b, that is the coefficient, the friction coefficient actually, and k, that is the stiffness coefficient, and we have x from 1 to 4, and we have x dot from 1 to 4. Let's run this to see if our parameters is in the workspace. Yes, they are. in the workspace, and we have all of the variables that we need to write these two equations here. So first of all, I need to comment out this line 7 here. So I start to code our equations. X dot 1 is x3, x dot 2 is x4, x dot 3 is equal to something here. Here we have something L minus M times cosine of theta, that is x1, and we need this to be in the parentheses to actually have our power here. And I think I made a mistake here. Let me code this line from first. We have something divided by something. We have 1, and we have L minus something. And here is something divided by something. In the denominator we have m plus m, and here we have m times L times something, and here we have something squared. In that we have cosine of x1, and here we have tau plus g times sine of x1 plus something divided by something minus something. Three minuses we have, so let's code them. Okay, here we have plus something divided by something. Here we have m plus m, and here we have f times cosine of x1. Here we have something divided by something, m plus m. We have b times x4 times cosine of x1. And here we have something divided by something, m plus m, and k times x2 times cosine of x1. And the last term here, that is this term, m times L times x3 times sine of something times cosine of something, x1 and x1. Let's run it to see if there is any problem. Okay, it's true. And we have x dot of 4 is equal to 1 divided by m plus m times something minus something minus something minus something plus something. Here is f, here is b times x4, and here is k times x2. This term is m times L times x2 times sine of x1. And this term is actually very similar to the last one. So we have something times something. Here we have m times L times cosine of x1, and here we can use this term that we code here for that parentheses in the base below here. So if we run the simulation, now we have our equations here. So let's code a for loop to linearize our model. Okay, for I equals to 1 to 4, we want to say that A of 1 and let me see, A of let me watch the equations. A of we need another for loop here for j equal to 1 to 4. Here we can say that the first one is for the rows, so we have to say I and j. The j1 is for the columns here, so is equal to diff of what? Diff of x dot of I with respect to x of j. Let me run this to see if it works. Size of A is 4 by 4. Okay. And the B term is equal to, let me code the B here. B is equal to something like this. And the B has to be 4 by 2. It is not 2 by 2. It has to be 4 by 2 matrix. So let's make it. Okay. Here is diff of f1, that is xd1, and our first input was tau, so we need to get derivative from xd1 with respect to tau, and the second one is we need to get derivative with respect to f, and here we need to do it for the second one, here we need to do it for second one and for f, here for third equation and tau, and here for fourth equation and f. Third one, the third equation. Yep. And here we need to get derivative from fourth equation with respect to tau, and here we need to get derivative from fourth equation with respect to f. Okay, let's run the simulation. Something is wrong here. Line 37. Okay, xt3. Oh, there is a problem, and now it's solved. Okay, Now we can see A and B in parameter actually form, parametric form here. So for linearizing, we linearize the model around a desired point for our states and for our inputs. So let's, for example, linearize our model around, I don't know, for example, um, the first one was theta, so 0, for example, 2 meters, 0 and 0. And here we can obtain our equations with the function of order here, subs here, sorry. So we can say that a num1 is equal to subs a, and the old one and the new one. The old one is x and the new one is x desired, and bnum, our B matrix is the B1. But now we need to have our linearized model x desired. Oh, we have typer desired. Okay. Oh, the size of x is 1/4, so here we need to transpose this here to have our a underline num1. Now we can see that we have our A matrix that is just is the function of our constant parameters here. So if we need the actual A and B, we can use these values here. For M, number is 6 kilograms, for example. M underline N is, for example, 1.5 kilogram. L underline N is equal to 0.6. K is equal to 0.75, and B is equal to 1.2, and G is equal to 9.8. And now we can say that A num is equal to subs A num1, the old one and the new one. The old one is M, L, K, B, and G. And here we have M underline N, M underline N, L underline N, K underline N. Oh, sorry. Here we need to define K underline N, B underline N, and G underline N. K underline N, B underline N, and G underline N. And for B matrix here, we need to change this to B. And if we were run this simulation, okay, we have an error here. Let's see what is our problem. M under 1, 2, 3, 4. Okay, we have an error subs A underline num1. Something is wrong here. Why? I'm trying to find the error. Let's transpose these matrices to see if anything changes. No, this is not the problem. So let's debug the code. The most important part of coding mechanical systems is debugging your code. So let's find out why we have such problem here. The error is something that I didn't encounter before. Cat arguments dimensions not consistent. Why? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. They are 6 parameters. Okay, let me change this to dd is equal to this vector here and run the simulation. When calling a function or indexing a variable, use parentheses. We cannot make vectors. Oh, understood. I think I understand this. Sim of d is equal to this, maybe. No, sims. No. Okay, M and B. They are some. I think we need to change this to. Oh, I think I understand the error. Here we need to have this in this bracket. No. This is correct. I know this is correct. Yes, it is. So here we need to say dd, and here we need to say dd as well. No, we cannot merge the symbolic parameters to each other. So let me change the code to this form, m and m underline n and m and m underline n to see if it works. Yes, it is. So we need to set values one by one. Okay, m and m. Here we need to have L and L, and also G and K. And after that we need to set B. Okay, let's run the simulation to see the results. B underline N has problem. Why? It is 1.2. Something is wrong with B underline M. Let's run the simulation. A underline num. We have a B parameter here that we want to substitute it with our value, but we got a strange error. Why? Why? I cannot understand. Oh, maybe for this B. No. No, no, no. Okay. I think you understand how to linearize the model. And actually now you can linearize the model of any systems. This is how it works. Thank you very much. Make sure that you subscribe this channel because I'm going to make a lot of videos about designing different controllers and modeling different dynamic systems and actually upload in this channel. Thank you very much.